Okay, welcome back. So the idea for today, this lecture, and also the next one, this is lecture 21. It's about compact spaces. So we are trying to study this notion of compactness. So this we described last time. The definition is something very, in principle, very kind of obscure, I could say. But the idea is space X is compact. If whenever you can write X as a union of some weird family of open sets, so each of these guys open, then you can actually rewrite that using a finite union. So you can disregard pretty much all of it. So you one union blah 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 union u I n for some family. So that's what we defined last time, and we also introduced some theorems. So let me open up the notes from last time. The first important thing was mostly we studied when Euclidean spaces are compact. The answer is pretty much never. So R to the K is never compact. The real line is pretty much never compact, but we discussed that any interval, that's not closed is going to be not compact. So this should be over here. So these guys are never compact. These guys are also not compact. And I promise you that at some point you'll prove that the closed interval AB is compact. That will not happen today. We're still going to assume it. We're going to prove that next time. And the main thing is after, and that's kind of the first problem with this notion is it's not that easy to come up with examples of compact spaces. But then when we introduce this theorem, namely any image of a compact space is compact, then we could very easily prove that we have a bunch of compact spaces, like any sphere, projective plane, for example, S1 cross S1. So we do know some examples at this point, and then we start proving theorems. So one that was very nice, the proof was very instructive, was this one over here. You start with a compact space and some subspace that's closed. Then subspace is also going to be compact. That's going to be very useful today. And another one, this is where we ended last time. If you take a Hausdorff space and you take something compact on that ambient, so it's just compact inside Hausdorff, then you need to be closed. So in particular, this will tell us something about what compact subspaces of the real line could be. They need to be closed. So for example, that's already, we know this, but this will be another way of proving that any half open interval cannot be compact. Okay, so first thing for today is we need to prove this proposition. So let me rewrite it here. This is proposition. Maybe let's get rid of this. So this will be proposition 4 from last time. And the statement is if X is Hausdorff, and you take a compact subspace, then this subspace needs to be closed. Okay, any questions before we start proving this proposition? Okay, so let's go for a walk here. What's the idea of the proof? Is instead of proving that Y is closed, we're going to prove that The complement is open. That's just the definition of being closed. So we're not really doing much here. And what's the meaning of this? What we want to show is x minus y is a neighborhood of all of its points. So we need to prove that if you take any point in x minus y, then there's going to be some neighborhood, some open neighborhood of the point inside x minus y. So let's fix something. Let's call it x naught in x minus y. And what we want to find, maybe let's say want to show, there exists some open in x that contains x naught, and is inside x minus 1. That will mean that's what we need to prove if we want to show that x minus y is open. So let me start with the ideas. So the first thing, at some point, we need to use pretty much our first assumption here. X is Hausdorff, so our space is Hausdorff. Whenever we take a point, let's call it y, little y in big set y. So what I'm trying to do is at some point I need to hook up an open cover for y and then use a finite subcover. That's what I'm trying to do. So I'm starting to hook up a cover, but we need it to be particularly nice. So for any y, this x naught is not going to be y, and the space is Hausdorff. That means there must exist two neighborhoods, one for x naught and one for y, but they depend on y because x naught is fixed. So there exists open sets. Then we call them uy and vy. The first one is going to, maybe I want to use y for the covers. So vy, uy, where x naught lives in v, y lives in u, and they intersect trivially. Oops, sorry. Vy intersection uy is empty. And that's because I have two different points in a Hausdorff space. So what am I doing here? I'm not really doing a lot. What I'm doing at this point is I will build upon this picture. So here's my y, the thing that we're assuming is compact. And here I have the complement, whatever that is. So I have a fixed point here, favorite point x naught, and I'm taking an arbitrary point here. So suppose I have a point here. And what I'm saying for that guy, I have a neighborhood of that guy and a neighborhood of x naught that they are not going to intersect. But maybe my neighborhood does intersect y. And we want our v, the v that we want it to be outside of y. So we need to fix this. So the idea would be we need to shrink this guy. The good thing is we can do this for each point here, and that's going to give us a cover for y. So that's the next step, since y is going to be the union of all these uys, right? That's both inclusions are clear here. The first one here is because, well, each ui is inside of y, and the second one is because each point belongs to the corresponding u. So that's a cover, since y is the union of these guys. And now we can use that y is compact. Oops, sorry. Yeah, I was saying something that's not okay. This y here is a subset of x, so these ui's are open in x, and this equality is not true. The only inclusion that's true is this one. But that's okay, because these guys are open sets in x. And we know from a lemma the last time since y is compact, we can just take finitely many of those. We actually have y inside finitely many of those. Blah, blah, blah. For some y1, blah, 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 yn in y. Okay, any questions? So here's a better picture of what's going on. Let me get rid of this one. I'll hook up a bigger one. Here's y. Here's x minus 1, the complement. Here's my favorite x dot. Now what I do is I start with, suppose a point here. Suppose that's my y. I can do this for any y. In this case, I know there is a neighborhood of this guy, like this, and a neighborhood of x naught, like that. Well, the important thing is x naught and the neighborhood for x naught and the neighborhood for y will not intersect, but x naught could intersect y. Now we can move on. We can take another point here. For this point, we're going to have a neighborhood, and also neighborhood of x naught. So something like this. Now we can move on. We have another point here, another y, neighborhood of x naught. They do not intersect, sorry. Something like this. And so on. But the crucial thing is, we only need finitely many points here to cover y because y is compact. So maybe with this orange, let's cross to the compact. So maybe we have something like this. And the idea is take this intersection. Wherever these guys intersect, this is what you want to take to be our B. And the good thing is, since we can only cover y with finitely many of these neighborhoods here, we don't need to take the intersection of all the B's, of all these B's. We only need to intersect finitely many of those. So here are the B's, here are the B's, here are the U's. And now my B is going to be the intersection of these guys, of these finitely many opens, sorry. So remember, this is what we're trying to find. And now I have a candidate. And we need to prove it satisfies all the properties. So let's prove it satisfies what it needs to satisfy. So first one is that it is open in X. Why is it open? Well, we're just intersecting finitely many open sets. So in fact, V is the intersection of finitely many opens. And that's the crucial part, because you could intersect all the V's, but that's probably not going to be open most of the time because you're just intersecting too many open sets. So V is the intersection of finitely many open sets. Part 2, V contains our favorite point x naught, our fixed x naught. And that's because, well, each V y contains x naught, and that's for any y, because x naught lives in Vy for every y in y. So in particular, it lives in each of these guys, or in each of these guys here. So we're safe. And for 3, and this should be the delicate one, V intersects y trivially. So this will mean that V is inside the complement. And that's the last thing we want. So how do we prove this? Shouldn't be that complicated. If we take, let's say, Z and Y, we need to prove C cannot live in V. So since Y is the union of the views, or is inside the union, we actually have that this C lives in some UYJ for some J. So one of these guys here. But the important thing is, hence, since UYJ cannot intersect VYJ, that means that C does not live in VYJ. And if you don't live in VYJ, you cannot live in V, because V is the intersection of all these YJs. And C is not in V. And this proves 3. So this proves X minus Y, capital X, and capital Y is O, because X naught is arbitrary. And we're done. That's exactly what we want to prove. So any questions? Okay, so that was the proposition. Let me go up to see what we proved. What we proved is, if you have a Hausdorff space and you take a compact subspace, then the subspace needs to be closed in the Lie space. So again, that should be useful. Now, what we're going to prove now is probably not an immediate consequence, but now that we have all these ingredients, the proof is going to be very easy. So this is a corollary, but I want to say it's a theorem. It's a theorem. It's not really a theorem, because we're just going to use things that we know to prove it. So let's call this theorem 1 for today. So suppose we have something that we've discussed a bunch of times. Suppose we have a continuous bijection. So continuous bijective maps. And here's the crazy thing. If X is compact and Y is Hausdorff, then the function here is going to be a homomorphism. That's great, because this means when you use the theorem, if for some reason you're going out of a compact space to a Hausdorff one, you want to build up a homomorphism, something that we did, for example, a bunch of times when we discussed quotients, then you only need to prove that you have a continuous bijective map. And the fact that F inverse is continuous is going to be automatic. So here's the proof. The proof is surprisingly easy. We just need to use things that we know. So only need to prove F is open. But this is equivalent to F being closed. So F being closed means F of C inside of Y is closed for every C inside of X closed. So it's enough to prove this. That's going to imply that F inverse is continuous. So now let's take an arbitrary closed in X. Let's call it C. And what we can do now is we just want to use our theorems from last time. So our X is compact. We know from last time that if you are a closed subset of a compact space, you are compact yourself. Since X is compact and C inside of X is closed, but by what we call proposition, let me find it. Yeah. So by proposition 3 from last time, C is compact. And now we're trying to compute f of C, but f is continuous. So since our f is continuous, we know that yes, f of C is going to be compact. Okay, but we're assuming y is Hausdorff. So, but the proposition we just proved, that's proposition 4, follows that you are a compact space inside the Hausdorff space. That means you need to be closed. And that's exactly what I want to prove. So that's the end. That's the end of this proof for this theorem / corollary. Any questions about the proof? A very short one. Just using things that we know. No crazy ideas. Okay, let me write examples and you will see how useful this is. So examples, let me use exponential to denote this function that we defined from the closed interval 0, 1 to S1, given by x, maybe only for space. So x of t is cosine of 2 pi t. We discussed this function a bunch of times. Here what we are doing is just going around the circle. So this is the circle and we're going around the circle using sines and cosines. And it's called exponential because this is a complex exponential when you see S1 inside R2, which is also C. So these are the two coordinates of the complex exponential. So we have this function x. The first thing I want to mention is we proved kind of carefully that when you restrict to open at 1, so we proved that x, but now going out of close at 0, open at 1 to S1 is a continuous bijection which is not open. We proved it's not open. And this is not contradicting our theorem because even though this guy here is compact, sorry, is Hausdorff, our y here is Hausdorff, then we go up to our theorem. Our y is Hausdorff, S1 is Hausdorff because it's inside R2, which is Hausdorff. This guy is not compact. So it's a continuous bijection, but not open. That's not contradict theorem. because what's going on here is 0, 1 is not compact. And that we know, not compact. Okay, however, we proved that this exponential function, I'm using bar, you know that's coming from quotients. So this descends to the quotient of the closed interval where I identify 0 with 1. This is the notation I used for the equivalence relation that only identifies 0 with 1. So we prove that the function descends to the quotient. I mean, it's not a crazy thing. We just need to prove that here at 0, you have the same that here at 1. So it's absolutely okay. Yeah, we prove that this function is continuous bijection. And I also claimed, we claimed with no proof, but we claimed that this function needed to be in homeomorphism. Of homeomorphism. And now we know it's true. We know it's true because this guy is compact. This is quotient of compact. So compact. And this guy is Hausdorff. So now we know it's true. Thus, we apply our theorem to this compact space, and it's compact because image of compact. Remember, we're still assuming this interval is compact with no proof. It's compact, and S1 is Hausdorff. So now we have a very formal proof that this quotient is exactly S1. Okay, now lastly, same argument I just did implies that, for example, S1 is homeomorphic to the real projective line, and the real projective plane is isomorphic to the two-dimensional disk, or the disk. This is the closed disk in R2. Here I'm identifying x to negative x if you live in the border of D2, which is S1. So this is apply the theorem. So apply theorem 1 to homework 5, part 5. So we had 2 questions asking us to give continuous bijections in this way. Oops. And in this direction. And remember, this is the symbol to denote 2 spaces are homomorphic. Okay, any questions? So this theorem is very useful, and it's something that I've been wanting to use for a long time. I'm very happy we get to apply it now. So now we want to move slightly to compact spaces and products of them. So the second theorem for today, we're not actually going to prove it, but I want to let you know what it is. So a product, so this should be theorem 3. The product X, no, I think it's theorem 2. Yeah, 2. x cross y. So I have two spaces, x and y. I compute the product with the product topology, which is also the box topology. We only have finitely many coordinates. So the product x cross y is compact if and only if, well, as you probably guessed, both of them are compact. So x and y are both compact. Okay. So to prove this theorem, we're going to need something that has this very fancy name, but makes absolute sense, the tube lemma. So the tube lemma, it's about neighborhoods of some things that are called slices. So let's take a product, consider x cross y, and I'm going to assume that y is compact. So by the way, I should say this direction is indecisive and only if the product is compact, then x and y are compact. That's clear because we have surjective maps from x cross y to x, namely project onto the first coordinate, and also to y, namely project onto the second. So we do know that if the product is compact, then both x and y are compact. That's kind of easy. What we don't really know is that if you start with two compact spaces, then the product is going to be compact. So here, I'm just trying to work towards that direction, this direction of the economy. And that's why it's absolutely safe to assume y is compact. So we have this setup, and now we fix some x naughts in x. And it's called the tube lemma because it's going to give me something that's called a tube neighborhood. So whatever we have a neighborhood, so n inside of x cross y, is an open set that contains, this is called the slice at x naught. So it's the slice because I'm taking x naught and I'm multiplying the singleton with the entire y. So in this case, if you are a neighborhood containing the slice, then there exists an open set in x that contains x naught. Maybe let's say such that x naught lives in U, and the entire U cross Y lives inside of N. So this guy is called the tube, and this guy is called the slice. And let me tell you why very briefly. So I will redo these big drawings in a second. So here's my x, here's my y. To illustrate this, I don't need to assume y is compact. So here's my x naught, some arbitrary point in x. Here's the slice. This is the slice x naught cross y. Right, all these points. And what we don't really know is what n is, but we know it's doing something like this. It's an open set that contains this entire slice. This is my n. And what we want to do with u is we now want to be sure that we have, let me zoom in here. We want to be sure that we have some little piece here. That'll be our u, such that when we take this tube, so go all the way down, all the way up, all the way down, we want that tube to be inside of that. So this is my tube u cross y. And I'm going all the way up and down because I have y here. So that's kind of the idea. If your neighborhood n contains this set, this slice, then it needs to contain a little tube, a probably very skinny tube, but it will contain. And probably from this picture, you can already tell why we really need the Y set to be compact, the Y space. Because otherwise, like your n could go like decreasing, something like this maybe. Your n could do something like this, get very close to x naught, very close to x naught, and then it's not going to be clear that we can. If you go all the way down, then I don't know what you could be. So any questions about the statement of the theorem? Okay, so now let's just prove the theorem. I will not use these parts. So let's prove the theorem, the tube lemma. Of course, the crucial thing here will be that our y is compact. So for the proof, let's just write what we know. Our set n, our neighborhood n is a subset of x cross y, is open and contains the entire slice. The slice x naught cross y. We know that for every little y, we do know x naught comma y lives in n. So this guy lives in n. But we're saying n is open. So it needs to be a neighborhood of any x naught comma y. And that means you need to contain a basic neighborhood. So let's call this basic neighborhood uy cross by. And now let me write this there. So for each y in y, there are going to exist open sets uy. Notice I'm using y for u and for b because they depend on y because x naught is fixed. So there are open sets uy inside of x and by inside of y. So definition of the box topology such that this. So x naught lives in u, y lives in b, and the product lives inside of n. So what's the idea now? Now the idea is something like this. Now I will need my new picture, where I do need to write the crucial fact that y is compact. So here's my y, but it is compact. So this is how I will remember myself y is compact. And here's my x. So here's my x, y, x naught. Favorite fixed, x naught. And again, we don't really know what it is. Here's my slice. Maybe I'll need to move this. Here's my slice. Slice n. Neighborhood n. So what I'm doing is fix your first y. That's nonsense. Fix some y. Then I have uy. I have uy cross by inside of n. Fix your second one. Also nonsense, but And again, you get something like this. And I want to kind of emphasize they could be getting smaller. And now you go down and do the same. They could be getting smaller and so on. They don't need to get smaller, but they could be. They could be getting weird shapes. Something like this, all the way down. So at some point, you might be here, very down here, with some very tiny open cell. But we know we can go all the way down. The important thing here is this Y is compact, and here we're covering Y with these guys. So just with these lines, we're covering Y. And that means you can take a finite count. So since Y is going to be the union of the VYs, so this here guys will be the VYs, and this guy here will be the UIs. Since this is an open cover, and Y is compact, what we actually know is that this Y is actually going to be the union of finitely many pieces, dy1, blah, 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 dym for some y1. So let me clear this page. There we go. So that's what we know. And now the question is, what's going to be our U? Remember, we're trying to, let me go up. We're trying to find U opening X, containing X naught, and such that the entire neighborhood, the entire tube, sorry, is inside of N. So what I should do here is I should kind of take the smallest possible U out of all the finitely many that we have, and that's expressed with the intersection. So something like this. Here's the smallest U, and then I take the tube. So let's write our U. Take U to be the intersection of these finitely many U's. UI, Y1, blah, 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 U, YN. And now we show it satisfies what it needs to. We show that's an S. U satisfies the three things it needs to satisfy. So the first one is we want U to be open. So it is open, well, just because we're intersecting finitely many open sets, because it is the intersection of finitely many open sets. So that's not very complicated. Second point is X naught lives in U. And that's simply because, well, because each, UI, because let's say X naught lives in UI for every Y in Y. So in particular for this Y1 through YN. Number three, and this is the important one, is that the tube U cross Y lives inside the given neighborhood of N. So what we're proving here, let me go up to the picture, is kind of showing that this tube is small enough so that we'll never go out of N. So this guy here is my N. That's the idea with this tube. So how do we prove this? Let's take, given, let's call this, let's take something here. Let's call this guy little u, comma, little y in u cross y. Want to show you, comma, y lives in n. So in this case, what we have is that y lives in y, which is the union of the p's, finitely many p's. So we can be sure that y lives in one of the p's, pyj for some yj, of the ones that I fixed before. But then, since u lives in big U, which is, remember, the intersection, so this is our important U, the intersection of the uy through uy1 through uyn, we know that u is going to live in that particular uyj. And in this case, u comma y lives, first coordinate lives in uyj, second one lives in vyj. But uyj cross vyj is going to be inside of n, because so uyj is inside of u, vyj is inside of y. Oh, but that's not what we want. Uyj, vyj. I'm here. I need to prove this guy lives inside of n. So I need to say that this lives inside of n. And this is exactly how we started our proof. Then you go back. This is exactly how we started with these guys. So that we know. And that's exactly what I want to prove. So that's the end of this story. Any questions? Okay, so we've only, yeah, let me stop recording.